Good morning. I am Dr. L.BHARATHI, Professor in AC Department, Sri Shanmugha College of Engineering and Technology, Sangagiri.
Today class, I would like to discuss about the measurement of acceptance angle and numerical aperture of optical fiber. Before we are going to discuss about the measurement of acceptance angle and the numerical aperture, let us go through the review of first part, that is first video, in which we have studied what is optical communications and what are the advantages of optical communications, what is optical fiber structure and how it will be, what are the different types of optical fiber and its structure, then how the light is traveling through optical fiber, you know it is based on total internal reflection and how total internal reflection occur, and what is a critical angle and what is Snell's law for refraction. These are the things just we have studied in the first part 1. Now let us go through the acceptance angle and numerical aperture of optical fiber. First, we should know what is acceptance angle. Angle at which the maximum light enters into the fiber. That is, maximum light enter into the optical fiber at a particular angle. That is known as acceptance angle, which is denoted by theta A, which is shown in the diagram. Let us go through the diagram to understand what is acceptance angle. Now, the light enters from air medium N to the interface of core and air medium at an angle theta A. The light then refracted into interface of N1 and N2 medium at point B at an angle theta C. Theta C is nothing but critical angle at which the light completely will be traveling through interface of two different media. It is not internally reflected back, it is not refracted into the cladding medium, only traveling through interface of two different medium. That is why the angle theta C is known as a critical angle, that is shown in diagram 1. Now let us go to the diagram 2. Here the angle, the incident angle is slightly more than the critical angle. Of course, as we know already, if incident angle is greater than that critical angle, the all the light or complete light will be internally reflected back and forth. That is, the total internal reflection is occurred. So the light ray enter into the fiber from air media at an angle theta A and refracted into the core medium to the interface of core and cladding medium and completely internally reflected back to the same medium, then again completely reflected back to the same medium. So like that, the light will be traveling through optical fiber based on total internal reflection at an angle theta A, known as a acceptance angle. So acceptance angle is nothing but half conical angle, half of the conical angle at which the maximum light enters into the fiber that will be propagating through fiber based on total internal reflections. Okay. Next, we will see that the numerical aperture calculation part. How can be numerical aperture calculated? As I told you already, numerical aperture is nothing but maximum optical power collected by optical fiber or maximum power gathered by optical fiber, known as numerical aperture. And it is also defined as sine of half of the angle of fiber's light acceptance cone. Within the half of the acceptance cone, the light is entered, the fiber is accepted, the light, so called it is numerical aperture. It can be derived in terms of expression. Therefore numerical aperture equal to sine theta A, where theta A is called acceptance angle. As per the Snell's law, n1 sin theta A equal to n1 sin theta. As we know already, n sin theta A, n is nothing but refractive index of air medium, theta A is the acceptance angle, n1 refractive index of core medium, and theta is the refracted angle into the cladding medium. So as per the two different media, when the light is entered from air medium to core medium, the equation coming to picture. Now the theta can be calculated. You can see that previous diagram. The theta can be calculated. The theta c, and this normal plane, nothing but 90 degree with respect to center axis of the core media. So theta can be determined. Therefore, theta equal to pi by 2 minus theta c, or theta c equal to pi by 2 minus theta. But we need, as per the expression, theta equal to pi by 2 minus theta c, or 90 minus theta c. Therefore, n sin theta a equal to n1 sin, you can substitute the theta here, 90 minus theta c. So sin 90 minus theta c, we know that cos theta c. As per that, we can substitute that value here. Sin theta a equal to n1 by n cos theta c. As per the trigonometry function, as we know all, sin squared theta c plus cos squared theta c equal to 1. Therefore, the cos theta c equal to square root of 1 minus sin squared theta c. Then the cos theta c, you can substitute over the above equations, as per the Snell's law, n1 sin theta c equal to n2 sin 90 degree. Now, this is one of the Snell's law, considering two different medium, the light enter here. Also, this is also one of the Snell's law, when the light enters from one medium to another medium. Here, air medium to core medium. But this Snell's law states that light enters from core medium to cladding medium. See, n1, this is theta c. Theta c is nothing but, critical angle at which the complete light will be travel only through interface of two different medium. At the time, that refracted angle become 90 degree. As we know already, n1 sin theta 1 equal to n2 sin theta 2. When sin theta 1 becomes sin theta c, when theta 1 become theta c, the theta 2 become 90 degree. Okay, now it is in critical situations. Therefore, n1 sin theta c equal to n2, since sin 90 degree equal to 1. Therefore, sin theta c equal to n2 by n1. Now, this sin theta c can be substituted in cos theta c expression. Already we have cos theta c equal to square root of 1 minus sin squared theta c. If we substitute sin theta c in the square root equations, we will get cos theta c equal to, cos theta c equal to 1 minus, 1 minus, so cos theta c equal to square root of 1 minus n2 by n1 whole square. As we know already, n sin theta a equal to n1 cos theta c, where sin theta a equal to n1 by n square root of 1 minus n2 by n1 whole square. Sin theta a equal to, square root of n1, square root of 1 minus n2 by n1 whole square, that can be expanded as a n1 squared minus n2 squared by n1 square. Okay, that n1 squared we can take it out, become, remove that square root, become n1, and that n come into the square root. So sin theta a equal to square root of n1 squared minus n2 squared by n. Then that n, as we know, by default become 1 because of refract index. Therefore, sin theta a equal to square root of n1 square minus n2 square. This is nothing but already we have determined, as per the statement, sin theta a equal to numerical aperture. So sin theta equal to numerical aperture, then na equal to square root of n1 square minus n2 square, where theta a equal to sine inverse of na, where na equal to square root of n1 square minus n2 square, where theta a and numerical aperture is nothing but acceptance angle and numerical aperture respectively. Okay, so here we conclude numerical aperture shows the light collecting ability of the fiber and its value must be high. Always the numerical aperture should be high, so that, maximum power gathering capacity of fiber can be determined. If we want to get that more numerical aperture of optical fiber, we have to get more acceptance angle. Okay, so acceptance angle, already we have discussed about theta A is nothing but acceptance angle, or we can say that this is a half of the conical angle theta A or acceptance angle. Now we go for the theta A can be rotated around the center axis of the fiber, it become acceptance cone angle, that is denoted by 2 theta A. So 2 theta A is nothing but acceptance cone angle. It is defined as acceptance cone is derived by rotating the acceptance angle about the fiber axis, which is shown in the diagram here. So the power or optical power, optical light enters into the fiber within the cone angle. The power can be traveled through fiber based on total internal reflections. If any light power will be incident or enter into the fiber more than that angle that is shown in dotted line, more than the acceptance cone angle, that will be refracted into the cladding medium, that will not come in back to the core medium. The refracted light will be disappear or dissipated when it is traveling through cladding medium. That is why we need to take carefully here, whatever the light enters the optical fiber, ensure that the light should enter within the acceptance cone angle or acceptance angle. Then the light, okay, the fiber can collect maximum power within the angle and support for the propagations. So here the light ray enter the fiber within the cone angle and travel through surface to surface and crossing the center axis of the fiber. This ray is known as a meridional ray. See here, already we know that the light is traveling through optical fiber from surface to surface, that is due to internal multiplication, internal reflections, sorry, not multiplication, internal reflection and crossing the center axis. So this type of ray is called it as a meridional ray. Generally the optical rays travel into the fiber, it categorized into three types. One is like meridional rays, another one is axial ray, another one is skew rays. There are three types of rays can be classified. Now what type of ray traveling through fiber from surface to surface and crossing the center axis, it is known as a meridional rays. And axial ray is nothing but a ray which will travel only along the axis of the core, which will not travel from surface to surface or any other place, which will travel only along the center axis of the core media. Whereas skew rays, ray which will travel along the fiber from surface to surface and not crossing the center axis, that is known as a skew rays. Of course, about details of skew rays we will study in the next slide or next video. Now we go for the numerical aperture properties. So of course we need to get more numerical aperture. In order to get more numerical aperture, we should get more acceptance angle. So that can be obtained by having, core refractive index and cladding refractive index. Okay, that is one of the very important parameter. The numerical aperture is not only depending upon the acceptance angle, it is purely depending upon the, refractive index difference between N1 and N2. Say for example, if N1 equal to 1.5, N2 equal to 1.498, maybe the difference is very minimum. If the difference is very minimum, of course refractive index is also minimum. If the difference is more, like maximum difference will be zero point 0.5. Why? Because the refractive index of the core media is 1.5. The refractive index of the cladding medium maximum of 1, almost equal to air refractive index, not below that. It maximum 1. So we can get 1.5 minus 1. Of course, we get maximum 0.5. So if we want to get this type of optical fiber without cladding, because cladding become air, so the fiber doesn't contain cladding medium. If it is the case, if the fiber is having only core medium, of course we get the more numerical aperture and acceptance angle, but we will get more signal loss. that should be avoided. In order to avoid the signal loss, we need to go for you know core refractive index as well as cladding refractive index. That is an important part here. We have to take care of it. So we should have little bit minimum difference in between core and cladding refractive index, not like a cladding become air medium. So we need to take sufficient acceptance angle and sufficient numerical aperture with very minimum signal attenuation or signal loss. This is the properties of numerical aperture. Now let us go for numerical aperture may also be given in terms of relative refractive index difference delta between core and cladding refractive index. See here, the delta is nothing but relative refractive index difference between N1 and N2. In terms of delta, we can determine what is numerical aperture, where delta n equal to n1 minus l2, nothing but refractive index difference, where del n by n1 is the fractional refractive index difference. Fractional refractive index difference. Hence, delta also approximate to the fractional refractive index difference. Therefore, delta equal to n1 square minus n2 square by 2n1 square, or it can be approximated equal to n1 minus n2 by n1. Here, delta is very much less than 1. As I told you already, the relative refractive index difference between core and cladding is very, very minimum, very much less than 1. Say for example, N1 equal to 1.5, N2 equal to 1.49. It may be very few. At this condition, we can say this fiber is weakly guiding fiber. The method is known as weakly guiding approximation method. This information can be studied in detail in the forthcoming videos. Next, we go for the equations. Numerical aperture can be determined in terms of delta. By comparing numerical aperture and delta equations, okay, Na equal to square root of n1 square minus n2 square, and delta equal to n1 square minus n2 square by 2 n1 square. By taking cross product, 2 n1 square delta equal to n1 square minus n2 square, where by applying square root here, n1 square root of 2 delta equal to square root of n1 square minus n2 square, or we can write numerical aperture equal to n1 to delta whole power of. Therefore, the core refractive index n1 and relative refractive index difference or fractional refractive index delta determines the numerical aperture, and it's very useful for measure of the light collecting ability of fiber or power gathering capacity of optical fiber. It is one of the very important parameter like acceptance angle and numerical aperture, okay, in optical communication system. The numerical aperture define maximum power gathering capacity of optical fiber, that is purely depending upon core and cladding refractive index or relative refractive index difference of numerical aperture. Now, let us see one or two problems about the calculate about the parameters what we have studied so far. The first problem, see that the refractive index of core and cladding material of step index fiber are 1.42 and 1.40 respectively. Calculate numerical aperture, acceptance angle, and critical angle at the core cladding interface. As we know already, what is numerical aperture? Na equal to square root of n1 square minus n2 square. What is acceptance angle? Acceptance angle theta A equal to sine inverse of numerical aperture. What is critical angle? Critical angle theta C equal to sine inverse of n2 by n1. As we know very well about the basic concept, based on the formula given here, you can find out what is numerical aperture, what is theta A, what is theta C. I have given here answer for the problem. Just you ask, you can substitute the values in those formula and try to get these answers whether it is correct. Okay. Next, we will see that something different kind of problem. As we know already, the relative refractive index is given here, whereas the relative refractive index is not given in the first problem. But with respect to relative refractive index difference, we can determine numerical aperture, acceptance angle, and whatever the parameters we need. See the second problem. An optical fiber has the core refractive index 1.36 and the fractional refractive index is 0.025. But cladding refractive index is not given here. Only core refractive index 1.36 and relative refractive index difference 0.025. You see that it is very minimum, very much less than 1. Okay, find the refractive index of cladding N2, then numerical aperture Na and acceptance angle theta A. These three parameters we need to determine for the given parameter fiber. Even here I have given only the answers. So with respect to the how to find out N2, how to find out Na acceptance angle formula, you try to get the answer for N2 numerical aperture and theta A. Then you check yourself whether the given answer is correct. This is what we have studied in the second video about theta A acceptance angle, Na numerical aperture. The next we go for next rays, different types of rays which are traveling through optical fiber. We can study in the next class. Thank you.